We are opening the second section of keynote sessions, and Jason Dai Big Data AI project makes it simpler to create large-scale applications with AI. Jason Dai is a main architect on AI and big data in Intel with a huge engineering.
You're welcome.
Hello, everyone. Hello, everyone. I'm Jason Dai from Intel. So my talk today will talk about our work in Big DL, which provides the end-to-end big data AI pipelines for our users to build large-scale distributed AI applications. So first, a few words about myself. I'm currently an Intel Fellow and the Chief Architect of Big Data AI at Intel. I have been working on the intersection of big data and AI, machine learning, deep learning, especially in the open source community for a long time, including Apache Spark project, as well as open source projects like Big DL and Analytic Zoom. At Intel, we're working very hard to make AI more productive for our users, for our developers, for the data scientists. There are different areas we have been working on, from the low-level libraries, optimizing the Python libraries, the AI deep learning libraries like TensorFlow and PyTorch, as well as a lot of libraries created by Intel, like OpenVINO and Ink. On top of the low-level libraries, we also provide various high-level toolkits to improve the end-to-end data science experience, to address the ML ops challenges, and to scale AI for distributed big data, especially the Big DL project, which will be the focus of today's talk. So, what is Big DL? Big DL is an open source big data AI project which makes it easier for our users to build large-scale distributed AI applications. So, if you look at this technology stack for Big DL, it actually consists of two layers, roughly speaking. At the bottom layer, it provides a horizontal end-to-end distributed AI pipelines. For instance, DLlib, which is a distributed deep learning library for Apache Spark, just similar to MLlib, but it's a library for deep learning algorithms. And the Arca, which is a library which built on top of DLlib but provides distributed TensorFlow, PyTorch, OpenVINO, and so on top of the big data stack. On top of these end-to-end distributed AI pipelines, we also provide various more vertical or domain-specific solutions or application frameworks for recommendation systems, for time series analysis, for PPML, privacy-preserving machine learning and data analysis. The stack, the Big DL stack, is built in such a way it can easily scale from your laptop all the way to your distributed class and to your cloud. So it is an open source project. We recently just put together Big DL 2.0, which is a unified project which combines the previous Analytic Zoom project and the Big DL project, and we merged the project in and released Big DL 2.0 as a unified open source big data AI project for distributed AI. Our goal with Big DL is to provide a unified end-to-end pipelines for distributed AI. Why is that important? Well, a key challenge when people try to apply AI to real-world applications is really how to apply those data analysis and machine learning, deep learning applications to your production data set, which you usually stored in some large-scale distributed data lake or data warehouse. The conventional approach is really you set up two separate clusters, one for big data, and one you're using Spark, Hadoop, and other big data stack. And after that, you will export the data and move the data to another deep learning cluster running, say, TensorFlow, PyTorch, and so on, and for the modeling. In this architecture, first of all, there is a lot of overheads related to data movement. And secondly, it creates a segregated workflow which makes the development very inefficient for the users. The vision for Big Data 2.0 is really you try to provide a unified big data AI architecture so that in the same cluster, in the same application, you may process your data, which is stored in a data lake or data warehouse, say using Spark. And on top of that, you can directly apply those deep learning or AI models, TensorFlow models, PyTorch models, OpenVINO models, and so on, to your in-memory, say, Spark data frame, which is an in-memory data set distributed across your cluster, and it can transparently apply those AI models, AI algorithms to your distributed data set, all within one cluster, and more importantly, one program, one workflow. With this type of approach, some of our customers, like Inspur, which is one of the largest hardware and software vendors in China, has seen their development cycle has been shortened from quarters to months. So this is really our vision, our goal with Big DL to provide these end-to-end pipelines for distributed AI. So next, let's look at some of the end-to-end big data applications, big data AI applications our user has been building on top of Big DL. The first example is time series-based network quality prediction in SK Telecom, which is the largest telecom service provider in Korea. So SK Telecom, as you can imagine, has a lot of base stations, 5G base stations, 4G base stations, and they collect network KPIs from those base stations every few seconds. So imagine you have hundreds of thousands of base stations, each streaming in many network KPIs every few seconds. So this is data set. This data stream is handled by a big data system consisting of Spark, Redis, LuckyDB, and so on. After network API KPI data get into the big data system, you analyze the data using Spark. After that, you probably want to build some AI models, for instance, TensorFlow models, to try to predict. In traditional fashion, previously what SK Telecom has done is essentially have two separate clusters. After you process the data in Spark, you export the data and ship it to another GPU cluster for AI training and inference running TensorFlow. This creates a lot of overheads in terms of data movement, and it also makes it very difficult to handle the new data. As you can imagine, you have those hundreds of thousands of base stations streaming new data every few seconds. This becomes very unmanageable. So SK Telecom has then used Big DL to build the entire end-to-end pipeline in a unified fashion. So you do the data pre-processing in Spark and Spark SQL, and then on top of those Spark data frame, it directly applies the TensorFlow model in a distributed fashion using Big DL. This leads to about 3x speed up for the end-to-end inference, and also 30 to 50% increase in the training as well. So if you're interested, you may look at the technical white paper, the link shows here. This contains more technical details of this time series-based network quality prediction for SK Telecom. Another example is Burger King, who have been building real-time context-aware fast food recommendations for their restaurant. So as the figure shows here, right? When the customer, for instance, drives the car to their drive-through restaurant, the customer looking at the menu board and place the order with the cashier. As the cashier enters the order, we try to build a model which look at the sequence of the order, as well as a lot of context information like a time of the day, location, weather, and so on. So we build a so-called transformer cross-transformer model to look at those information and predict what are the other items the customer may likely to order and show it on the menu board. As you can see, there are additional items displayed on the menu board, which is shown as a recommendation. So with the entire data analysis, data pre-processing, and distributed training, the entire unified pipeline built on top of Big Deal, Burger King can actually improve their sales by quite a bit. You may look at the technical blog as well as those our previous technical talk for more details. The last example shown here is how Alibaba leveraged Big DL PPML to build privacy-preserving machine learning applications on Intel Xeon, especially Ice Lake Xeon servers. So Big DL PPML provides a trusted platform for the users to run large-scale distributed data analysis and machine learning and deep learning applications. All the data and all the compute, all the models can then be protected by a combination of hardware security technology like SGX as well as software security technologies, so that it allows our user to run trusted, secure data analysis and AI applications, even on untrusted, say, public cloud environment. So I just show some of the examples how our users and customers have been building various different applications on top of Big DL, from recommendation to time series analysis to privacy-preserving machine learning. And there are many other cases like Mastercard, like JD.com, and so on. If you're interested, there is a link at the end of this talk where provide more use cases as well as technical talks. Our users have been presenting their use cases. So next, I will provide some deep dive on how our users, most those data scientists, so data engineers, so the machine learning engineers, can actually use the libraries in Big DL to build this end-to-end distributed big data AI applications. So first, let's look at some code examples. So what do we mean by provide end-to-end pipeline for our users to build distributed AI applications? Roughly speaking, at a high level, there are actually 3 steps for our user to do that. First of all, you need to process your data, and usually this means you have a large-scale data set which are stored in some distributed data storage, whether it's a file system, it's a data warehouse, it's data lake. So the first step is how do you process your data in a distributed fashion. You can use, for instance, Spark data frame, as shown in this example, if you are a big data engineer, a big data user. For a lot of data scientists, they actually prefer to use Python libraries like TensorFlow dataset, PyTorch data loader, or maybe some of the PyData libraries like the sklearn, NumPy, or maybe PyImage data library like a Pillow and OpenCV. So in Arca, in addition to Spark data frame, we also provide a distributed Python APIs, which allows users to write their data processing, use those conventional single-node Python libraries, but them can be executed in a distributed fashion across classes using the distributed Python API in Arca. So once you process your data using the distributed data processing APIs, the next step is how do you build the model? In this case, the user can actually use standard TensorFlow or PyTorch libraries to build their model. So the example shows a TensorFlow example, but you really can use TensorFlow, PyTorch, Keras, and so on. The beauty of this approach is that now you can actually write your TensorFlow, PyTorch code directly in line with your big data, say Spark program. And in the third step, Arca provides a scikit-learn-style API, a estimator API, which directly takes your distributed dataset, for instance, Spark data frame, and your deep learning model, a TensorFlow model or PyTorch model, and provides transparently distributed training and inference support. So in this case, with this example, it takes a Spark data frame, and then takes your Keras model, and the user just needs to call estimator.fit, which under the hood essentially replicates the model across your cluster and feed each local partition of the data frame into that model, run the local model forward and backward, and then it runs a highly efficient or reduced type of parameter aggregation and to aggregate parameters, update weight, and it runs in many iterations, train your model in a distributed fashion. All those details has been abstracted away from the users. The user can directly, from a user program point of view, they can just directly apply a TensorFlow PyTorch model to your distributed, say, Spark data frame, and get a model trained or get a model inferenced. Well, this is just the first step. How do you write your code to build your distributed AI pipelines? But there is equally more, or if not more challenging part, is how you deploy your application from a laptop to a distributed cluster. Usually, any data science project just starts with a single, for instance, Jupyter notebook on your laptop. So how Arca provides support for you to seamlessly scale from a laptop to a distributed cluster? First, you can create a container environment on your local laptop or workstation, install all the libraries, all the Python libraries you want to install, you want to use. Then you can use the API we just demonstrated in the previous page to build the end-to-end pipeline on your local laptop. You process the data, create a model, and use an estimator to train a prediction. After you're happy with your code, basically this code can run on your local laptop. So you have a Jupyter notebook on your local laptop, and it can just run on your local laptop. You may want to do some prototype with that code with some sample data. After you're happy with that, you will usually need to launch a job in a class environment to run this notebook in a distributed fashion. This has actually been a pain for a lot of the data scientists, as there is no easy way for them to take a single node Python notebook and run it in a distributed fashion on a cluster. And so you usually need to rewrite the code and so on. So what we try to accomplish in Arca is really with one line change, you can deploy your notebook running on your laptop to a distributed cluster, whether it's a Kubernetes cluster, a Hadoop cluster, a hosted cloud environment. So at the beginning of your notebook, you just call a method in its context, which tells the program, tells the library which environment you want to run, whether it's on a local laptop, so it's a local cluster, or it's a Kubernetes cluster, and so on. So just with that one line code change, the notebook can run on your local laptop and can seamlessly scale to a distributed cluster to process a large scale data set in a distributed environment. So this is the second aspect, how you can build the end-to-end AI applications to provide seamless scaling. So the previous two slides talked about how you can use Orca and the DLib can actually build your end-to-end applications for your big data analysis and AI applications. Next, let's look at some of the higher level, the more vertical domestic solutions built on top of those pipelines. The first is really PPML, the privacy-preserving machine learning. And so there is it provides a trusted platform, leveraging the hardware security technology as well as the software security technologies to provide a secure, trusted cluster environment for users to run large-scale distributed big data and AI applications. There are really two use cases our users have been using PPML for. The first, as I mentioned before, you can launch a big data PPML to provide a trusted cluster environment for you to run unmodified big data analysis and AI applications. So essentially, one of the most typical use cases, really, a lot of our users want to move to cloud, public cloud, but then there are a lot of confidential and security requirements before they can actually move their sensitive data or sensitive computer model into the cloud. So with big data PPML, they can actually create a trusted platform, trusted environment on the cloud. You have all the data and the model encrypted, and so before you put it onto the cloud, so all the storage can be protected by all the encryption technologies. And then when you try to run your application, run your model, run your, say, Spark SQL data analysis, you need to read the data and decrypt the data. And all those compute and the memory are protected by the hardware, the X enclaves, which allows basically a subset of the memory can be only accessed by the program running inside the enclave. No one outside of this enclave can actually look at what is going on there, what is the memory, what is the data in the memory, what is the compute, and so on. This allows the compute and the memory to basically it can support those unmodified data analysis and machine learning code you have already built in your environment. Now you can run it in an unmodified fashion, but at the same time it's protected by all the hardware and you cannot access it from outside of the enclave. And then since you need to do large-scale data processing and machine learning, you will need to do it in a distributed fashion. So all the network communications in the distributed computing is protected by both remote attestation as well as TLS type of security encryption. And finally, again, all the user request, user response, the result of your query, maybe the result of your model inference, and so on, are protected by TLS encryption as well. So in this way, we leverage a combination of hardware technologies as well as software technologies for security, so that we can create a trusted platform, trusted class environment, even on an untrusted environment, say public cloud, which allows users to analyze their data using big data analysis and machine learning, but without data or compute or model exposed. That's one scenario as I just described. The other one, another scenario really, for a lot of the users, they just cannot have their data leave their firewall. They have to have their data stored in their own organization. But on the other hand, they do want to train a model jointly with other parties. For instance, a typical use case is a bank maybe collaborate with a online retail service provider. So they have so for a particular user A, the bank may have some of the information, and the retail service provider has some other information. And if you can combine those information, you can train a much better model for fraud detection, for recommendation, and so on. So in this case, Big Data PPML provides a so-called trusted federated learning, especially vertical federated learning, in the case that each party has a subset of the feature, a subset of feature for a particular user of a particular item, but they can jointly train a model without revealing the data to other parties. So this a lot of those federal learning support combined with the SGX security enclave, we can actually provide another level of security protection against adversary parties in this federal learning scenario. In addition to privacy-preserving machine learning, another important use case we have been working with our customers really large-scale recommendation. So a lot of our customers like Burger King, I just showed previously, have been building large-scale distributed recommendation systems on top of Big DL. And to support those type of users, we have built Project Fusion, which is the application framework for large-scale end-to-end recommended solutions built on top of the end-to-end distributed AI pipelines we just described. So if you look at the recommendation solution in Fusion, it really consists of three components: the offline, nearline, and online. So let's look at this example. In this example, we have a lot of data, right? We have 40 million plus users and 300 million plus items, and we try to. The goal is really when a user comes in, we try to get what are the most relevant items we can recommend to the user. Maybe he or she will like, will click, will buy, or maybe will forward to others, and so on. And then the offline component really works on the distributed feature engineering training. So the latency is really on hours, right? You get the raw data, and you run the distributed feature engineering to generate the user features, the item features, and then you train the model to generate first a recall model. In this case, we use a two-tower model for recall, generate user embedding and item embedding, and a ranking model. In this case, we are using a winding deep model to generate a ranking model to do the prediction. After that, those user features, those features and embeddings are being loaded into the in-memory system like a Redis, or maybe a vector search system like a Face. And the models, the ranking model, of course, is loaded into a model system, a model store. The nearline component really allows the user to do near real-time update, especially when you have a new, for instance, when you have a new item, a new user comes in, you want to generate a new feature or embedding for them, or in some cases you may actually incrementally update your model. So it's usually in an order of seconds to minutes, you can actually update the model to create a new model. And then the online part is really doing the online serving. It's a real-time serving with, as I mentioned, with the user ID comes in, you want to look through the system to pick, you have 300 million items and you want to pick maybe the top K items which you think are most relevant to the user. And this needs to be done in the order of 100 milliseconds, basically below 100 milliseconds for each request. So the online serving party really has multiple services. The recommended service takes the user ID and go to the recall service, which use some vector search type of capability system to find the most likely items, and then it go to the feature service to get the features for the user and for the likely items, and then all those user and the features go to the ranking service, and which runs the model inference and generates the probability. And then the result is sent back to the invoker, which actually may go through some business rule and business policies before the final result is shown to the user. So this essentially is the architecture of Project Fusion, which try to provide a large-scale end-to-end recommendation system building on top of big deal, those end-to-end pipelines, as well as a lot of big data and AI components. And finally, another important type of application people have been building on top of big data is real-time series analysis. So in big data, we have actually provided Project Cronus, which is an application framework to build large-scale distributed time series analysis using AutoML technologies. So in Cronus, it has, first of all, it has a lot of built-in algorithms for those time series and data. For instance, TS dataset for a lot of time series data processing, loading, scaling, and so on, and also a lot of built-in models for time series prediction and anomaly detection. With that, the user can directly build their time series applications using TS dataset to process the data and use the built-in model to do forecast anomaly detection. But to get the best result, to get the most accurate result, we also provide a AutoML capability which takes those built-in algorithms and look through those search space, including what are the most best hyperparameters to use, what is the most best model to use, and all those different model selections, feature selections, and hyperparameter tunings. And this is done through Ray Tune and the Ray on Spark, which is a capability we provide in Orca, which allows the user to run Ray directly on top of a big data cluster, and so that you can use big data to process your data and then run the AI algorithm, in this case, hyperparameter search using Ray on Spark. So in this case, it's run many different trials, each trial with a different set of parameter, hyperparameter, and model settings, and it's try to use different algorithms to try to find the best model and parameters. So, for instance, some of our users are actually previously using Profit, a popular time series algorithm, and then which is actually very difficult to tune because it has a lot of parameters you need to hand tuning, and using Cronus, it provides a built-in auto profit support, which takes the profit model, take the profit algorithm and your data set and automatically tune your profit algorithm. So that's actually one particular example of how our user has been using Cronus for time series analysis. So if you are more interested, you can refer to our previous talk at Usenext AutoML last year, so it has more technical details. So in summary, BigDL is an open source project which provides end-to-end big data AI pipelines to make it easier for our users, the data scientists, the application engineers, to build large-scale distributed AI solutions, and to make it even easier It also provides various vertical frameworks like recommendation, time series analysis, privacy-preserving machine learning to help our user quickly put together their complex solutions. So it's an open source project. You may check our repo at the GitHub. And as I mentioned, there is a lot of different users like Burger King, like Office Depot, Mastercard, SK Telecom, Alibaba, JD.com, and so on, who has been using big data to build various big data AI applications. So you may refer to our blog. There is a lot of blogs in the Power BI page, as well as a lot of talks or presentations in the various conferences. And if you are really interested in the technical details, you may also refer to our tutorials, previous tutorials like CVPR and SharePoint, as well as our technical papers at ACMS OCC. So that's all I have to cover in my talk. Thank you, and I hope you'll find it useful. And as mentioned before, it's an open source project. You're welcome to look at our source code and to download it and have a try. Thank you.
Mr. Dai, thank you very much. Thank you for your report and your presentation. And would you be so kind to answer some questions that are coming right now from our viewers for you? So the first one, which framework is best for a new big data and AI project, Apache, Spark, or Ray? What do you think of it?
Well, it really depends on your use case, right? The problem is really how I can apply very complex data processing, larger scale distributed data processing, and that's actually one of the key challenges here. Then Apache Spark is probably the best framework today. It's the one that is production quality, deployed at many customers, and battle tested, and has all the capabilities for you to do large scale distributed data analysis. If your use case is really, I want to do a lot of advanced AI algorithms, like reinforcement learning, like hyperparameter optimization, hyperparameter searches. Yeah, Ray actually provides those advanced distributed AI or machine learning capabilities for you to do that. So that's why in Big Data we actually Big Data is built on top of both Spark and Ray because we believe each one has its best fit. So there is a, as I mentioned, actually previously talked in my slides, there is a library called Ray on Spark, which allows the user to run the Spark program and the Ray program side by side, and then you can feed your Spark dataset into a Ray cluster, and so that you can process your data, distribute the dataset using Spark, and then use Ray to run the AI algorithm on top of it. So we have actually customers running reinforcement learning on the dataset which is processed by Spark.
Okay, the next question, can Big DL be deployed on Kubernetes clusters?
Yes, I mean, Big DL can run on Kubernetes, can run on Hadoop, can run on your cloud environment, and it also can run on your laptop. Yeah, a lot of our users, I would say maybe 50% of our users actually run Big DL on Kubernetes in production today.
Where can services with SGX for privacy-preserving machine learning be found in Russia?
I'm not sure about the particular service providers on that, but Intel's latest Xeon service, the Ice Lake codename Ice Lake service, actually has SGX 2.2 support with large unclaimed memories, allows you to do very large scale data analysis and processing. I think maybe you can. I'm sure there are a lot of Intel people in the conference. You have probably talked to them on the details.
Okay, and the last question: can the Kronos project be used in personal projects?
Well, it's an open source project, as I mentioned. It's an open source project. You can go to our website. You can go to our. There is a lot. You can just download it on your laptop. As I mentioned, it can run directly on your laptop. And we also provide a bunch of notebooks you can directly open in, say, Colab, Google Colab, and can just without any installation, you can actually run your Chorus or any other big deal applications there. So yeah, definitely you can do that.
Okay, thank you very much. Thank you, Mr. Dai. Thank you for being with us.
Sure, thank you.
Bye-bye.